Hello, chemistry students. We're going to continue our conversation about compound stoichiometry. Only this time we're going to talk about one-step dimensional analysis. Okay, when working with moles, molar mass can be used as a conversion factor. And we're going to use this while performing calculations with dimensional analysis. How many moles are in 28.7 grams of lithium nitrate? So the first thing you're going to do when we do our dimensional analysis now is we are going to write what we know. 28.7 grams of lithium nitrate. Now we need to find out what lithium nitrate looks like. The formula, because we don't write lithium nitrate over here, we write the formulas. Lithium is in group 1, so it has one valence shell electron, and it's a metal, so it is going to have a +1 charge. Nitrate is an NO3 with a -1 charge. Since +1 and -1 add to be 0, the formula for lithium nitrate is simply LiNO3. So we're going to put LiNO3. Now we are looking for moles, so I'm going to draw my dimensional analysis grid here. I have grams of lithium nitrate, but I want to go to moles of lithium nitrate. So I'm going to write moles of lithium nitrate over here. Now I want to get rid of my grams, so in order to do that I need to put it on the bottom, because if there's one on the top and one on the bottom, they go away. Now if you look at this, grams per mole, that should tell you right there that we're looking for molar mass, grams per mole. So now we need to find out what the molar mass of lithium nitrate is. Lithium is 6.94, and we have one of them. Nitrogen is 14.01, and we have one nitrogen. And oxygen is 16.00, and we have 3 of those. So 3 times 16. And then we're going to add all of those together. That happens to be 68.95 grams per mole. So now I just need to know, do I put this number on top or do I put it on bottom? And if it is grams per 1 mole, it is going to go on bottom next to the grams. So 68.95 grams per 1 mole. Now we are going to take away our grams of lithium nitrate, because if you've got one on top and one on bottom, they go away. And you are left with moles of lithium nitrate, which is what you want to be left with. So now we're going to do 28.7 times 1 divided by 68.95. Just to remind you, if anything's on the upper part and it's between a line, you multiply them. If it's below a line, you divide it. So the answer is 0.416 moles of lithium nitrate. Now let's do our next one. We're starting out with 100 grams of aluminum sulfate. So I'm going to put that up at the top. 100.0 grams of aluminum sulfate. And I need to go to moles. So I'm going to go ahead and draw my dimensional analysis grid, and I want to end up with whatever's on top over here. Moles of aluminum sulfate. This is what I want to end up with. I need to get rid of this grams of aluminum sulfate, so I'm going to put it down here. Grams of aluminum sulfate. And if we look right here, it tells us what number is going to go here. So we have grams per mole again. That is molar mass. So we need to find the molar mass of aluminum sulfate. Aluminum is 26.98, and we have 2 of those. So we're going to go 2 times 26.98, and we have 3 sulfurs. So I'm going to go 3 times 32.07. And we have 12 oxygens, because 4 times 3 is 12, so 12 times 16.00. So I went ahead and multiplied all these out and then added them all together to get the molar mass of aluminum sulfate, and I've gotten 342.17 grams per mole. So I need to know if I put that number up here or down here. Well, it's 342.17 grams, so it needs to be next to the grams up here. So 342.17 grams in 1 mole. Per mole is divided by 1. This is the same thing as saying 1 mole down here. So now our grams of aluminum sulfate go away because it's one numbered or one unit divided by another unit. They cancel out and we're left with moles of aluminum sulfate, which is what we want to be left with. So when we take 100 times 1 divided by 342.17, we get 0.2923 moles of aluminum sulfate. That is our answer. Now I have 4 significant digits here because we have 4 significant digits here. So if I tell you to measure out 1.34 moles of water, how many grams will you pour? So what we want to do here is we start out with 1.34 moles of water. Well, by the way, the abbreviation for mole is simply MOL. It's not much of an abbreviation. You just take off the letter E. And we want to end up with grams of water. So I'm going to put grams of water over here. Now I need to get rid of the moles of water, so I need to put that on the bottom. Okay, and if we look here, grams per mole of water means we need to find out what the molar mass of water is. Hydrogen is 1.01, and there are 2 of those, so 2 times 1.01 is equal to 2.02. And we have 1 oxygen, which is 16.00. So the molar mass of water is 18.02 grams per mole. So do we put this on top or do we put it on bottom? Well, it's 18.02 grams in 1 mole, so it's going to go on top because it needs to be next to the grams. 18.02 grams in 1 mole. Now our moles of water go away and we're left with grams of water, which is what we want. So it's 1.34 times 18.02 divided by 1. And that answer is 24.1 grams of water. Now I have 3 significant digits here, so that's why I cut it off at 24.1 and had 3 significant digits here. How many grams are in 2.8 moles of oxygen? Now remember, oxygen is diatomic, which means it looks like this. Okay, so what we start out with is 2.8 moles of oxygen, so that's what I'm going to put up here on the left. 2.8 moles of O2. And what I want to end up with is going to be over here on this side, and I want to end up with grams because that's what I'm looking for, grams of O2. Now I need to get rid of the moles of O2. I have it on top, so I'm going to put it on bottom. Now this tells us what number we're going to put here, and it's grams per mole, which is molar mass. So we need to find the molar mass of O2. Oxygen is 16.0, and we have 2 of them, so it's 2 times 16, which is 32.00 grams per mole. Now, does it go on top or does it go on bottom? Well, the 32 grams in 1 mole, so it needs to go on top. The 32 needs to go next to the grams, which is right here. And we put 1 on the bottom. Now our moles of oxygen, we have 1 on top, 1 on bottom, so they cancel out, and we're left with grams of oxygen. If we multiply this out, 2.8 times 32 divided by 1 is going to be 89.6 grams of oxygen. There's your answer. Okay, now we have 256 grams of a pure monoatomic element, which means there's only 1 of them. And it is known to be 8.26 moles of that element. What element is it? Well, if we look at the periodic table, we can tell what an element is by two numbers. We can tell it by its atomic number. Can we get the atomic number from these two numbers right here? No, we cannot. The other way we can possibly tell is from the atomic mass, because each one of these elements' atomic masses are different. Can we get the atomic mass from these two pieces of data? Well, atomic mass is given in grams per mole, which means if we have the mass of something and we have the moles of something, all we have to do is divide them and that will give us the atomic mass. So we have 256 grams. And we have 8.26 moles. And I have grams per mole, so this is going to be good. That gives us a number of 30.99 grams per mole. So now what we're going to do is we're going to look on the periodic table for a mass, an atomic mass, an element that has an atomic mass that is very close to 30.99. If we look at that, this is the closest one, phosphorus right here, has 30.97. It is not exact, but it's pretty darn close. It's closer than any of the other two that are next to it. So we are going to choose. So our element is phosphorus. Okay, we need to restate Avogadro's number and its meaning. What is Avogadro's number? Well, it's 6.02 times 10 to the 23rd particles in 1 mole, per mole. It is the number of atoms in 1 mole of a substance. That's what you've learned so far. 1 mole of a monatomic element is equal to 6.02 times 10 to the 23rd atoms of magnesium, because we have our element here is magnesium. So in 1 mole of the element magnesium, there are 6.02 times 10 to the 23rd atoms of magnesium. Just to give you an idea of how big that is, I'm going to drop down here the Mg, which stands for magnesium. Now this will drop down in 8 seconds, and it is 775. So if we sat here till we counted 6.02 times 10 to the 23rd, now this is 775, and it takes 8 seconds to count 775 for our computer, we will be here 197 million years. A million times, by the way. You'd have to do 197 million years to sit here and watch the magnesium go that quickly a million times. So it's quite a big number. Now 1 mole of a diatomic element, O2, or a covalent compound, H2O, is equal to 6.02 times 10 to the 23rd molecules of oxygen or water. 1 mole of any ionic bond, for example, NaCl, sodium chloride, is equal to 6.02 times 10 to the 23rd formula units of NaCl, or sodium chloride. So now we're going to talk about or do some problems on calculating formula units, atoms, and molecules. It says, how many formula units are there in 7.55 moles of sodium sulfate? Well, we're going to start out with 7.55 moles of sodium sulfate. I'm just going to write this out for you. And we want to end up with formula units, okay? And I'm not going to write formula units. I'm going to abbreviate formula units, and that is FU. Na2SO4. Now I need to get rid of this moles of Na2SO4, and in order to do that I need to put it on bottom because I've got one on top. Put it on bottom. Now if we look at these units right here, it will tell us what number we're going to put in here. So we have formula units per mole. That is the same thing as particles, by the way. A formula unit is the same thing as particles. So we are going to use Avogadro's number, which is 6.02 times 10 to the 23rd particles. And in this case, our particles actually stands for formula units per mole. So now we got to ask ourselves, do we put the number on top or do we put it on bottom? Well, this is formula units per mole, and when it says per mole, it means per 1 mole. So we're going to put it on top, 6.02 times 10 to the 23rd formula units in 1 mole. Now we have a mole of Na2SO4 on top and a mole of Na2SO4 on bottom, so we can cancel them out. And our units are Fu, or formula units of Na2SO4, and that's what we want it to be. So now we do 7.55 times 6.02 times 10 to the 23rd divided by 1, and that gives us 4.55 times 10 to the 24th formula units of Na2SO4. That is our answer. Now we're asking how many moles are in 8.24 times 10 to the 23rd molecules of water. So we start out with 8.24 times 10 to the 23rd molecules. So remember, whatever we start out with, we put over here on the left. Now our abbreviation for molecules is MLCL. So we have 8.24 times 10 to the 23rd molecules of water, and we're trying to go to moles of water. So I'm going to put moles of water on the top at the end because this is what we want to end up with. So we need to get rid of molecules of H2O, so I'm going to put that down here. Now these units right here tell us what we need to put here, what number. So we've got moles per molecule or molecules per mole. That should give us a big hint that we're going to use Avogadro's number. And in this case, instead of particles, we have molecules. Okay, so our MLCL stands for particles here. So we have 6.02 times 10 to the 23rd molecules per mole. Does it go on top or does it go on bottom? Well, it's going to go on bottom. The number's right next to molecules per 1 mole. So the 1 goes on the top and Avogadro's number goes on the bottom. Our molecules of water go away because we've got 1 on top and 1 on bottom, and we're left with moles, which is what we want, and that ends up being 1.37 moles of water. Now remember, I am taking significant digits here. This has 3, so my answer can only have 3. I'd like for you to pause and do the next 2 examples on your own. Go ahead and check your answer. Now go ahead and pause the video and try this problem and then check your answer. Go ahead and check your answer now.